All right, good morning, everyone. It's my pleasure to be here today with you and to share some lectures. And Brian, how do we pull up the lectures now? All right, perfect. All right, so thank you for coming to this lecture to learn how real qubits really work. It's really my pleasure to be here today, and as Brian said, I'll pause every 5 or 10 minutes or so to take your questions, because the next 3 hours are really your time. The next 6 hours of my lecture will answer what is a qubit, the kind of superconducting qubit you may have already logged into in the cloud and experimented on. How can you design, control, and measure a real superconducting qubit? And also I'd like to focus on the question of why. Why are these the right important questions to ask? I think these are valuable and practical stepping stones that you will need in your career in quantum to be successful. And the next 6 hours of these lectures will give you the ideas and the skills needed to grow in this field. So what lies on the road ahead for us today? As you can see, it's a windy road, and we'll start over here at the very beginning, and we'll chart a narrow path, but a very deep and long path, meaning we'll go pretty far, but start very introductory. The first topic I'll get into is, what's the big picture, right? Going between your computer through a system in the cloud, through some devices, superconducting qubits in this case, all the way to the Bloch sphere. Or in other words, how do we take the Bloch sphere and actually realize it in practice? And that will bring us to the second part, which is quantum physics and the physics of real atoms, the quantization of energy levels, and the fact that there are actually no qubits. There is no such thing as a real qubit in life. There are only two-level approximations where we can usually take two levels from a much larger system and pretend that it's a qubit. But it works really well. In the case of the kinds of superconducting qubits that you have been experimenting on and playing with, that will take us into discussing what is the transmon qubit. It's the prototypical or the main bread and butter superconducting quantum bit, which implements these two levels that you play with. And now also you can explore these higher levels using some new features like Qiskit Pulse. And that will allow you to take advantage of a lot more physics and potential that we haven't really been able to explore before with just two levels, but we can now leverage the much larger space of possibilities. Now, to really describe what a superconducting qubit is, or what a real atom is, or an artificial atom, I'll go back and review the classical circuit theory and the classical harmonic oscillator. This will be very familiar to most of you, but I'll try to add a bit of a twist to how we see it and try to build a little more intuition, which can help guide us on our path leaping into the quantum. Unveiling the quantum oscillator, or the quantum harmonic oscillator, which will be the building block of all the tools and all the superconducting devices, both transmon qubits, the way we read them out, the way we control and manipulate them, and as some physicists like to think or say, they're really only spins and oscillators, and everything else just reduces onto a spin or an oscillator. And finally, that will lead us into the last hour of the talk, which will be on the details of the transmon qubit, going from the basics of how do we move from the harmonic oscillator to actually a nonlinear or so-called anharmonic oscillator, look at its wave functions, the way it's described, and then its experimental signatures. how would it look like in a spectroscopy experiment? How do I control it to do a Rabi rotation? How do I calibrate it? Right? All of the practical questions, all of the stepping stones needed to actually build the logical circuits that we implement, the control NOT gates, the Hadamard's, etc. And also to take advantage of the more rich and dynamic space in which the qubit exists and lives. And that will be for today. And tomorrow we'll pick up with measurements. Now, this lecture I view as both introductory and skill reaffirming, meaning we'll take a big step back. You don't really need to know much going in, but we will go far. We will go quite far. That means that some sections will preview advanced material. I'll try to label those and denote those with the Donald Knuth's dangerous bend symbol. So if this is the first time you're going through some of this material, you can skip past those or just take a cautionary sign here. And the idea is that we'll use examples, simple, basic examples, things you've probably already seen. However, these examples serve as stepping stones to very practical problems in the very practical way that we actually realize qubits. And the idea here is to extract the macro from the micro. The very simple things we will illustrate today really carry over and describe most of the physics of the entire field. They're just the roots of it, and everything else grows on top. And so I will try to be as step-by-step as possible in the derivations and in the way I go from a classical circuit to a quantum circuit, or from the quantum circuit to the transition spectrum, and so forth. Of course, please ask questions or write your questions down and post them in the channel. Brian will get those to me as soon as we can. And finally, this is very tightly integrated with lab work by Dr. Nick Braun and co. I'll try to avoid the fire hose of information, and someone shared this graphic with me when I was trying to prepare this lecture, and I thought it was a good reminder to try to chart a narrow path and focus on a few key points as much as possible while exposing you to the much larger picture. So let's begin with the big picture. I think all of you at this point from the first few lectures in the summer school have seen that a qubit consists of two energy levels, typically denoted by a 0 ket and a 1 ket. Energy levels were a picture proposed by Niels Bohr in 1913. Now you saw that this picture is a bit of an abstract thing, and the way that these quantum states actually get represented, or the really physical, distinct number of distinguishable potentially states are infinite, and we can represent them on the Bloch sphere. Now finally, how does this very abstract picture of energy levels in Bloch sphere actually occur in the cloud? All right, now this is a picture of a real device, one of the devices I think you may log into, and this is a fridge. Now, not the kind of fridge, of course, you have in your home. This is a very, very expensive fridge that can go to very low temperatures for reasons that we'll see in a minute. But the quantum bit, the actual physical quantum bit, sits at the very bottom of this fridge, and everything else is input-output wiring. In the more recent days, they have, of course, turned to look quite a bit more stylish. And this particular case, housing this fridge, was done by the same company that does the Mona Lisa, and I thought that was very cute. Now, what's inside of this fridge? Let's take one of these dilution fridges and zoom in, unveil what's inside of it by removing the outer can. And that usually shows us a picture that looks very much like this. We call this the golden chandelier. And this is a superconducting dilution fridge inside, where you see a lot of cables going in and out. It is actually gold-plated. The point here is, though, that everything that is quantum really sits only at the very bottom in this little in this little shield at the very, very bottom of the fridge, and it operates at 15 millikelvin. That's negative 273.13 Celsius, and we'll see why that temperature has to be so low. Now, inside of this shield, unveiling several other shields, you see a picture of a chip like this. This is a superconducting qubit chip, and what you see here is a device with a number of quantum bits, qubits, which we'll delve into today, which are housed on this substrate or chip back here, which can be silicon or sapphire or some other dielectric, and a number of readouts. These squiggly superconducting coplanar waveguides indicate readout resonators. And as I'll discuss in the rest of this talk, the superconducting qubits are also a type of resonator, a type of microwave resonator. And in this lecture today, we will focus on how do we create and define the quantum bit or qubit. If I zoom in on the picture here, it's this little structure composed of these two metallic pads connected by some sort of inductor or nonlinear wire that it actually supports the physical picture of the Bloch sphere. And we'll talk a little bit about an intermediate step of the representation, because these, at the end of the day, are oscillators, microwave oscillators or electromagnetic oscillators, oscillations of the electromagnetic field, which we can represent using circuits, perhaps the kind of circuits you studied way back when. Except that now these are going to be quantum circuits, and we'll see how we can make a transition from the classical world to the quantum world and describe the very unique features of quantum with these circuits and how they allow us to support the Hilbert space in which we do the logical computation. And at the end of this lecture, we will derive the Hamiltonian, which describes exactly how this qubit originates. That brings us to circuit quantum electrodynamics and qubit in the cloud. So let me give you the big picture of the summary of the flow. You have a laptop which you might log into, which can then send some information that controls a fridge. Inside of this fridge, at the very bottom of this dilution refrigerator, sits the qubit chip. This qubit chip then allows you to support, in the abstract sense here, we're now moving to the abstract, electromagnetic circuits with electric and magnetic fields, which themselves allow you to create this type of Bloch sphere and then to control it, manipulate it, and so forth. And they also allow you to measure it so that information can flow back from the Hilbert space all the way through the circuit, up the fridge, and to your laptop and back. And so this closes the feedback loop. And today we'll focus on how the qubit originates from this circuit, as well as how we can really connect the very physical picture to the very abstract Hilbert space. And I think this is where I'll pause for questions. So let's see, Brian, if there are any questions yet.
Two questions. I want to remind everyone, if you have questions about things not related to Zlatko's lecture, such as labs, final project, any of that, please use the Discord or email me. We're not going to be able to spend time answering those during lecture. So, a first question we have here about Zlatko. This is kind of a personal question for you, but the question is, what's your personal favorite flavor of superconducting qubit and why? And maybe you could also add in if there's any cutting edge kind of superconducting qubits that that aren't fully functional yet, but that you are really interested in. Maybe share some light on those as well.
That is an unexpected question. Thank you. I have two flavors. I have the flavor that I like to sit down and write everything about, which is the one I'll describe in this discussion today. It's called the Transmon qubit. It's perhaps the simplest qubit, and I like the simplicity of it because it allows you to illustrate pretty much most of the general ideas very simplistically. More generally, yes, I like the very exploratory superconducting qubits, and most of all the ones we haven't anticipated yet. including the hybrid ones. Of course, the fluxonium is a favorite of mine that I've measured and played with a lot. And now people are very excited about the 0 pi qubit and variations of it. So that gives you a little bit of a flavor of it. I don't get the ice cream with the one scoop, but with the several scoops.
I love it. All right, I think that's one for now. We'll let you go back to your lecture and find more questions later on.
All right, thank you. And I'll try to point out some differences between maybe the very simplistic transmon qubit we have here, which is the bread and butter of, and actually what you log into through Qiskit, but maybe also some of the variations to what other types of qubits look like. All right, so that brings us from idea to reality. Let's get into some of the concepts. Again, the qubit implements two levels and a Hilbert space. Right? These are two pictures that are interconnected. For the more advanced of you, I've left a little question/note down here for if you're interested in this. Now, for the rest of us, how do we realize these two levels in practice? And so that will get me to talk about real atoms. And let me back up to get everyone on the same page. So for the more advanced students, I apologize, but I hope this will get us all on the same page. And all the way back to the origins of quantum physics. Imagine a cloud of atoms, right? Each of these pictures here is an individual atom, and this is essentially how all experiments in physics, quantum physics, were done until circa 1980. Now you can take this cloud of atoms, put it subject it to some excitation, such as a voltage source here, and it will glow. It will shine. You can feed that light through some lens, some thin ribbon, and a prism. The prism will split out the different frequency components of the light. And what physicists observed is that the light that gets split out from the cloud of atoms comes out only in certain colors, such as red, green, purple, and so forth. And so if you look at a spectrum of the light, and this is an actual measured spectrum of H2, you'll notice that you get very discrete, distinct colors, lines. This motivated people to look at various atoms, and they noticed that each atom had a different structure. Hydrogen had one set of discrete lines, helium had a second set, neon had a third set, sodium a fourth, and so on. That led Bohr and company to propose that atoms are different from classical mechanics in that the energy can only take certain discrete amounts or levels, can only be in certain discrete levels. And this helps explain why the transitions appear in these discrete and not continuous emissions. So the atom can only emit at a particular frequency because the energy can only be either 0 or 1 and not 0.5, nothing in the middle, so to speak. That's the colloquial language to say it. Of course, you'll recognize this in the recent July 4th fireworks some of you may have seen, and each of the different fireworks has different atoms, which of course give off a different set of frequencies. All right, and that brings us to the atomic energy levels and transitions. An atom, quite often for the electron, has a potential energy landscape of 1 over r, and so this is where you can write down the potential energy, say as a function of the radius, and it typically goes like something 1 over r, where r is the radius between, say, the atom and the electron over here, the atom nucleus. And this potential, now normally in a regular system, the atom can have any energy. It could be a particle here, here, or here. The idea is that in quantum, of course, these energy levels are quantized, denoted by these red lines. Now, they're not just quantized in any way, they're quantized in a very special way, what we call anharmonic. Anharmonicity means that the energy levels are not spaced equally. What that means is that if you apply a laser that shines some microwave light or optical light at the atom, and the atom starts, say, in the ground state and is subjected to a force that tries to steer the atom from the ground state to the first excited state, Once the atom is in the first excited state, because here I'll assume that the frequency of this laser is tuned exactly to the transition frequency between the first and 0th level, the atom can then no longer steer the atom from the first state to any other higher level here because of the antiharmonicity, meaning that there's no level that the frequency of the laser can take this atom to that's up above, where the height of this arrow represents the frequency of the laser. That's very special because what it means is that when we shine this atom, it really only acts or interacts, when we shine the light, it only interacts with the atom when it's in the lowest 2 energy levels. And this allows us to isolate a qubit subspace, right? And for a real atom to really just work with the lowest 2 levels. So that's the basic idea of then how you take one of these atoms into a 2-qubit subspace. It's also very important that this atom is isolated from the environment, so the thermal fluctuations and noise in the environment doesn't destroy the quantum coherence and quantum properties of the atom. Okay, and its energy level diagram allows for very specific control and also for very high and good readout. The atom in that sense is low loss. However, again, a main message here is that it's not a 2-level system, and there are no 2-level systems. In reality, there's always a coupling to some other degree of freedom, which really creates more than 2 levels. And that will be exactly the case as we move into the superconducting world. Atoms are very nice, however, they come with certain properties. And we'd like to be able to engineer everything about the atom. So my personal flavor of atoms is artificial atoms, created by electromagnetic circuits, which can mimic the electromagnetic properties of atoms and also have quantized levels. And so that will bring us into, very quickly, the next section. Brian, are there any questions at this point?
Yes, I am going to go through and pick up. We've got a lot of good questions, but I think one that maybe we want to tackle right here at the beginning is actually, I saw 4 or 5 people ask the same question about the chandelier itself. You showed the gold-plated chandelier and you explained that this is our quantum computing setup, but a lot of people actually didn't understand there's a lot of loops, the gold itself. Yes, exactly, that picture. So I was hoping if you could walk through and explain to people why it's gold-plated and what all those loops actually do.
Yeah, great question. Thank you. So it's gold-plated because we like gold. No, it's gold-plated because gold doesn't rust, because gold is an incredibly good thermal conductor, and because it's soft. Basically, the gold has very nice material properties, which are very nice for things like thermalization and preventing. So why thermalization? Notice that at the very bottom here I said this operates at 15 degrees, so 0.015 Kelvin above absolute zero. Up here at the very top we operate at 300 Kelvin, room temperature. There must be some source that's cooling this thermal load at the bottom to this temperature, and that's in the mixing chamber, which is, I think, somewhere here in the back. In order to create a thermal link that can take away the heat from this element to that cooling source, we need to have a good conduction, something that doesn't isolate between the very cold and the very hot. And so gold is a very good thermal conductor, and it allows you to press 2 metals very hard together and get a nice thermal contact, whereas a hard metal usually doesn't allow you to do that. It also doesn't oxidize very much, so it has a very thin oxide layer which you can break through easily, which helps with the conduction. All the loops also have to do with thermalization. When things get cold, they tend to change in size. And as the fridge changes in size, as you heat it up and cool it down, it stretches. And if you have a very taut metal cable, it can get snapped quite physically. It can get pulled apart from its connectors. And so the loops allow you to give some mechanical flexibility or pliability to the cable as you have thermal shrinking and expansion. Thank you, Brian. Was that answering the question?
Yep, perfect. Back to you.
Perfect. All right. Okay, so artificial atoms. These artificial atoms will consist of capacitors and inductors, and I'll spend quite some nice time talking about that. Now, very much like the anharmonic degree of freedom, the harmonic oscillator that is set up by an inductor and capacitor, which allows electromagnetic energy to slosh back and forth between the capacitor, which say has negative charges and positive charges flowing back and forth, and we'll get into that in a minute. It has a potential energy landscape that looks very much like that of the atom in a way, except that it's typically quadratic. In, say, the charge, or in what I like to think of here as the magnetic flux across that coil. This quadratic energy landscape also has only finite levels that quantum physics allows you to get into, and we'll derive exactly what those are. If we now couple this circuit to an input-output transmission line, something just like the laser that allows you to guide waves in and out of the structure, to subject it to forces and control it, you notice that if I send in a microwave or a wave at a particular frequency, let's say omega 01, that's the frequency of this wave up here, if the atom starts in the ground state, then the microwave light has energy. It can transfer a photon that takes it from the ground state over here to the first excited state. Now, once it's in the excited state, if I keep shining the light, that laser can again provide it another photon of energy that can stimulate it to go up to the next level, and up to the next, and so forth. In other words, I have no individual control that allows me to isolate the lowest two energy levels here. I cannot isolate this level and this level, just like we did in the atom. And that's because the spacing between these lines, you notice, is equal, or harmonic, in other words. And that's why in this talk we'll introduce a nonlinearity, which will open up the potential and make it softer as the particle climbs in energy. And so we'll make this inductor, a tunable inductor, a nonlinear inductor, tunable in the sense that its inductance will change as a function of how much energy is stored in it. And that will open up this potential and allow us to isolate the atom of the qubit in the lowest two levels. And that's really the core idea of everything we'll discuss in the next 2 hours and a half, except we'll go through a lot more technical rigor and detail and physical pictures of how this actually happens and how do we describe it and what are the consequences and how this really shapes what a logical qubit is for us today. Okay, so then to summarize the very big picture overview, there's the idealization of the qubit, which has two energy levels, say 0 and 1. And this Hilbert space is really realized in an anharmonic oscillator, which has transition frequencies between energy levels that are not equal to each other due to a nonlinearity. The way that that anharmonic oscillator is created and modeled is through a circuit, which really describes a physical device. Real electrons moving in real metals and supported by real dielectrics. And so we move from the level of idealization to the level of physical reality. And in the following, I'd like to spend a little bit more time discussing the physical reality and then take us all the way back up to the idealization. In the rest of the talk for now, I'll focus on these two parts. And that brings us to circuit quantum electrodynamics, where I'll give a bit of a macroscopic overview Now you've noticed that we've moved away from spins quite a bit, more and more towards oscillators. And I like to discuss this joke with my friends. There are two kinds of physicists: those who believe all of physics is spins, and those who believe all of physics is oscillators. Maybe you can guess which one your host today is. Now, as we saw, the ingredients of circuit quantum electrodynamics really consist of microwave oscillators, which come in a variety of shapes, forms, sizes, and so forth, such as these coplanar waveguide oscillators, these squiggly lines here, which we will describe today at the quantum level, as well as these transmon qubits, which implement the nonlinear anharmonic oscillators, which provide the actual superconducting qubit. All of these physical devices we can represent with very simple lumped element model circuit elements such as capacitors, inductors, which you've probably seen in your high school physics class, and of course Josephson tunnel junctions, a key ingredient to the nonlinearity, which is low loss and very well behaved, that I'll get into in the later part, as well as the input-output elements that can allow you to control and measure these. And the goal of circuit quantum electrodynamics is to combine these elements, just like you can combine the same ingredients and make them into a burrito or a taco or a different flavor of food, in various and unique ways, and essentially form the basis of most of our field. Now, at this point, you might be asking yourself, wait a minute, these are just circuits. I've seen circuits. What's so special about them? How are they quantum? Well, is your microwave quantum? And you might say, it doesn't, you need low loss. Quantum systems are very precarious. I need to have very little dissipation. Well, a microwave is actually not too bad. It has a quality factor of 10 to the 4. So the microwave mode in there is pretty high. But it also needs to be isolated from the environment, right? Thermal fluctuations need to be very, very low relative to the frequencies of interest. And this is why a microwave isn't a quantum object, because the temperature is so much higher than the energy spacing between those levels. So essentially, all quantumness gets washed out very quickly. A microwave is also not quantum because it lacks nonlinearity and doesn't have a lot of and we'll see that one more aspect that's important for circuit quantum electrodynamics is large quantum vacuum fluctuations. And I'll define what those are in a minute. So to get all of these nice properties, we need superconductivity, which will allow us to have small dissipation, isolation from the environment. It works at low temperatures already, so that gets taken care of. However, we also need to have nonlinearity, something that creates a nonlinear potential so we can have anharmonicity. And for that, we'll use the nonlinear and very robust effect of the Josephson tunnel junction, for which Brian Josephson predicted and won a Nobel Prize for. And to give you more of a picture of where does this all physically sit in the large scheme of things, here's a picture you may have seen from NASA, which describes the wavelength of electromagnetic light, the frequency of electromagnetic light, which goes all the way from sort of radio frequency up to microwaves to Wi-Fi and goes into the visible light and all the way towards X-ray and gamma rays up here. And we can relate the frequency to an effective temperature of the body through black body radiation, or maybe through the simple equation here. And I can give you an order of magnitude of where things sit. The fridge has to be at the lowest temperature. The environment in which the superconducting qubit operates sits at about 10 to the minus 2 Kelvin. So roughly here in the temperature range, very, very close to absolute zero. The superconducting circuits we'll operate with have frequencies, resonant frequencies, on the order of 10 gigahertz, which is about half a Kelvin, which is much larger than the fridge temperature, but as you can see is really, really low energy relative to visible light or really most of the other electromagnetic phenomena we see in our everyday life. And the wavelength of these is about 3 centimeters. The optical transitions you see in fireworks or get controlled in atomic nuclei tend to be in the visible spectrum and have a much larger range. But the photons and the energy we'll talk about today in microwave oscillators is in that sense very low energy. And in the next slides, I'll get into a lot more detail. And for those of you who want to see more depth or follow up with more reading, here are a few references you can pause in the playback and dive into after this lecture if you're interested. And that brings us to the world of circuit quantum electrodynamics. And Brian, I think I'll pause and take any questions.
Okay, so one question before we dive into any of the hard science questions, which I know are coming. So if you've asked one of those already, just hang tight. But just one final question kind of about the setup that we at IBM have chosen to use. One person was asking, with all the different candidates, why is it that IBM decided to go with superconducting qubits?
That's a good question. I guess there's a story there, which may be written up somewhere, but the research group here, of course, well, IBM has a very long history with superconductivity. It really pioneered some of the early work on superconducting classical processors and has quite a spectacular fab for superconductivity and a lot of expertise in this field. So there was a natural point of connection and transition there from the early days of Josephson junctions, and a lot of the key research back in the day was done at the facility that we work at today. And in the 80s and earlier days, quantum effects in those junctions and those nonlinear circuits were completely ignored and really out of reach. But with the advent of technology and science, we were able to isolate those circuits, minimize the noise, reduce the temperature enough, and start to understand their quantum behavior and show that, in fact, a superconducting circuit, a circuit which consists of billions of electrons, can actually behave macroscopically as a single degree of freedom, just like the position of the electron around the nucleus. And these effects, I think, then led to a very exciting new field, which said, wow, you can suddenly create your atoms as you want, artificial atoms in a way. You can engineer the energy level diagram in any way you want, something you can't really do with real atoms. They come in the varieties that they're given to you. And superconducting circuits have, as I'll show at the end of this talk, had a tremendous trajectory in terms of their growth in coherence times and control parameters. And of course, they're in a way the most analogous to classical computers. So, naively you can see a path to scaling to large architectures very quickly, because they use microlithography, nanofabrication in very much the same way that conventional computers do. And so that motivates a nice analogy between classical computers done with CMOS technology and quantum computers, which when done with superconducting circuits are also on silicon chips and metals and so forth. And I think that they are particularly exciting and very promising. So maybe that gives you a bit of the flavor.
Perfect. Back to you, Blacko. Thank you very much.
Okay. Good. That brings us to the world of circuits. And to do quantum, you often have to start with classical. And in part that's because in quantum, a lot of things have a really nice analogy that can be really understood in classical physics very well. So we're going to spend some nice time on a classical oscillator, which will really explain a ton about the quantum oscillator. And we'll go over some very basic things you may have seen, but with a twist. Here's a transmon qubit in the picture of a real device. Let me show you now a picture of a transmon qubit that I've drawn here as an illustration, kind of zoomed in, where you see that we have a substrate, which is some sort of dielectric, such as silicon. There are two metal pads, just pieces of metal on top of it, just like a classical circuit so far that you might find in your iPhone or Android or what have you. And somewhat specially, these two metallic pads of the superconducting transmon qubit are connected by some sort of inductor, which here I've just depicted for illustration purposes as a box. And in general, this will be some kind of nonlinear inductor, such as a Josephson tunnel junction, which we'll get into later. Now, let me give you a bit of a physical picture as to what actually happens and why this is an oscillator in the first place, and what's actually oscillating. These metal pads, of course, have many electrons, and by applying an electric field across them, you can create a displacement where you shuttle some of the positive or negative charges from one island to the other island. And so these green circles here indicate a net positive charge. The red circles indicate a net negative charge. Typically in one of these metallic islands, there are about 10 to the 12 mobile electrons, to give you an idea of how many electrons are involved in this. Now, in practice, this is going to be at very low temperature, which means that these electrons condense into superconducting pairs, so-called Cooper pairs, and they move without dissipation. We can label the charges on one island as plus Q, and they can vary on time, and the charges on the other island as minus Q. Of course, there's conservation of charge. Charge doesn't get destroyed or created, so we can only slosh charges back and forth between the two islands through this little bridge. This variable Q, which will describe the charges, has support on the full real line. Of course, an electric charge, a net electric charge, creates an electric field, which in general depends on position and time. It can oscillate. And if you have an electric field, that electric field can then be used to define a voltage between one pad and the other pad. So I can say that the voltage here, and this is not a detail you need to get very acquainted with, I just want to illustrate the bigger point, but the voltage here is related to how much electric field lines link one pad to the other pad, and it goes from RA, which is pad A, to RB, which is pad B. It doesn't matter which way you draw it. And the voltage is again a number between minus infinity and infinity. Now, there is something very special about this particular structure, and that's that because the frequencies we'll operate at are relatively low compared to the inner modes of the structure. In other words, the wavelength will be very large compared to the dimensions of this little transmon, which, by the way, is, the dimensions here are about 100 microns across, so they're relatively small. This transmon is these two metal pads are in the so-called lumped element regime, and we can model them as a very simple capacitor you've seen before. Feynman has a very nice discussion of how this happens between Maxwell's equations and this very simple relationship here, where you can say that the charge in one island is related to the voltage by a value C, where C is called the capacitance, and it's a number between 0 and infinity. And of course, we denote that in electrical language with a symbol like this. If a charge moves from one island across the bridge to another island, that creates a current defined by the positive test charge here moving across. Of course, it leaves behind depletion. And moving across to this island, it changes the charge. Because charge is conserved, we can, of course, write down this universal relationship that is valid for all quantum circuits, which says that the rate of change of charge on the island is equal to the current, in this case the current through this junction. Or equivalently, that the charge is equal to the integral from the start of the world, so to speak, the start of the circuit, all the way to the time t. It's just integrating how much charge has gone left or right through this bridge, keeping track of it. In circuit theory, we keep the initial conditions fixed at minus infinity. T minus infinity is just a label. It could be t equals 0. It's some reference state, but we'll keep those initial conditions 0. And the current, of course, is also on the support of minus infinity to infinity. Now, for the more advanced of you who've seen some of this material before, I'll just draw a cautionary tale that we have chosen the reference direction of the voltage and current opposite to each other, and that's important for later writing the Lagrangian in a nice way. Now, what happens when a charge tunnels or travels from one side of one island to the other side of the other island? It can create an electromagnetic field. Moving charges create magnetic fields, and a lot of magnetic fields can create a magnetic flux. The magnetic flux we denote by this variable phi of t. It can be related to the voltage across these two metal pads by a very simple relationship. This is essentially a lumped element version of Faraday's law of induction, and it's a universal relationship, one that holds for all circuits, for all branches, independent of their nature or constitution. The magnetic flux is, again, the time integral from the reference state to time t of the voltage, just like the charge. And similarly, the rate of change of magnetic flux, or how many of these magnetic field lines are here, depends on the voltage between these two metal plates. And we'll pick again for the initial conditions that the flux is at time 0 equal to 0. And the magnetic flux lives on an infinite support between minus infinity and infinity. I'm emphasizing here the support of these variables where they're actually mathematically defined, because quite often in circuit theory there's a question as to whether the variable across these two pads is compact or non-compact, meaning does it go between 0 and 2 pi because these are superconductors, or can you just use a variable that goes from minus infinity to infinity. And there is a very simple, again, relationship that I recommend Feynman's book on, which describes that you can, in the lumped element regime, link the magnetic flux phi to the current that flows through this junction, with L being the inductance. And Brian, maybe I should pause and take any questions at this point?
Yeah, I'm looking through. We had a lot of questions coming in at a pretty wide spectrum, if you will, of answers. But I've seen a few people asking about the bridge that you're discussing right now. In fact, I know this is probably a straightforward question, but they want to know, is that bridge itself acting as an inductor?
Thank you. Absolutely, yes. So, great question. So this bridge here, and I've purposefully not specified what kind of bridge it is, because it could be anything. It could be a linear inductor, it's just a piece of wire. It could be a Josephson tunnel junction, which is a superconducting element. It could also be a nanowire. It could be an atomic point contact. It could be a variety of things. But the essential thing is that whatever it is, it has some relationship, inductive relationship, between the current that flows through it, the amount of charge, and the magnetic flux that gets established. And that constitutes an inductor. So the orange bridge here is the inductor.
Awesome. Thank you.
Good. And I see that we're coming up on 10 o'clock, so I think maybe we'll take one or two more questions and then head for a 10-minute break.
Sure. Let's do one more question. I'm just going through, going through right now. I'll give you the top voted question. Can we use a quantum computer? So it's a little off topic, I apologize, but can we use a quantum computer to find the path of least action in a Lagrangian mechanics? I'm sorry for mispronouncing that so poorly.
Oh, Lagrangian mechanics, I presume?
Yeah, that's the one.
Yes, that is an interesting question. Well, yes, you can set up an optimization problem. I guess it depends maybe a little bit on how complicated your problem is, but in principle, yes. We will get into Lagrangians in a couple of slides after the break, which will be our path and stepping stone towards a Hamiltonian description. First, the classical Hamiltonian, which will very quickly turn into a quantum Hamiltonian. And that will lead us to describe exactly this structure you see here in much more detail. Of course, underneath all the theory, what I haven't described or won't describe in great detail is that we're optimizing an action integral or a particular path. Although I will introduce the classical action angle variables very briefly, which we'll talk about that, which will be the analog of the quantum bosonic ladder operators, the raising and lowering operators, A and A dagger.